Okay, let's get started. We have a lot to do. Chapter 5 is a big chapter with a lot of important material in it, and we've only got 4 weeks left in the semester. And in those 4 weeks, we've got project number 2, Chojuk Bairam, Spring Mayfest. So we're going to be pushing to try to get through it. We maybe have to go a little faster than the normal tempo on the slides. But I still would like for you to raise your hand and say, sir, could you please explain this, or I didn't catch this. Doesn't mean you lose your right of asking questions, of course not. But I might have to pick up the tempo just a little bit to make sure that we get through the necessary material. I hope that you are reading now in Chapter 5 and you're aware that we're in memory now and you're following along. That would be the best thing to do, would be to be keeping up with the course. The other thing is, I hope that your group is already meeting and you're starting to work on the design. Don't wait till the end, the last weekend. It's too big to pull out real quick in a short time. As I hope all of us learned on the first project, tempo la, yani chalisha damle gololur, right? So not pat die hepsi birden, right? So you got to have to work at it. So plan your time. One of the things that was very common when I and Ozcan Hoja asked students, so what was the thing, if you could do differently, you would do different about this project? Almost all said, manage my time better, start earlier so I don't have a big crisis at the end. So if that's what you learned, don't just say, keshke and not change. Change your strategy in order to manage your time better, okay? That's the thing to do. And if you find the other people in the group are still procrastinators, let's wait till Sunday night, we can do it in one night. Tell them they're crazy and tell them you're going to do it without them, okay? The project needs to get moving. If people are slow and they don't get their act together, then that means their personal participation is low. The project team needs to move forward. Everybody here has a lot of leadership capability. Why don't you just take that project team and start pulling them up the hill? It's a steep hill. If you all say at the bottom, oh, wow, that's a big hill. Yeah, well, let's wait till we all feel like it. You're never going to get up the hill. Somebody's going to have to charge up the hill. Bite the bullet, as we say in English. Bite the bullet. You know where that came from? Before there was anesthesia, when they had to do surgery on soldiers, they said, here, put this in your mouth, and then they cut. And you bite the bullet in order to not break your teeth. Bite the bullet means take the pain and get going, all right? So when I hear groups saying, oh, we haven't had our first technical meeting, we just, got our little contact report together, that's all we did. And I say, what, the weekend's gone? Now we're already to Tuesday, you haven't done anything? No, we're going to get started later this week. How long are you going to wait? Okay, so that's my charge to you, is get moving. This is the design phase right now. The design phase. If you do a bad design, then the rest is not worth it, because how can you implement a bad design? It will not work. You got to do dirt Luke work in the design phase in order to have a chance that the implementation would do something. All right, so I'm telling you things you already know. Take the lessons from Project 1 and apply them to Project 2. It's the same Suraj. Design first, then review, then implement, right? Okay, so that's all I'm going to say about the project, but get moving. Get moving. Have your meetings right away. Don't waste time. Okay, let's get back to Chapter 5. Okay, Chapter 5, exploiting the memory hierarchy. Okay, memory hierarchy. Let's study the memory hierarchy. Sounds like a nice little passive observation. No. We're going to exploit. Do you know what exploit means? It's like to use for your advantage. To exploit means to get the good stuff out of it. We're going to exploit the memory hierarchy in order to do what? In order to do what? What's the big P word that we've always been talking about for 2 semesters practically? Performance. Of course, we're after performance. We're going to exploit in order to get performance. So first we've got to talk about what is the memory hierarchy, then we're going to learn how to exploit it. Now normally I don't believe in exploiting people, but I believe in exploiting memory hierarchies, okay? If you know the deep meaning of the word exploit, it means to use it for your gain despite the zarar to somebody else. I don't believe in exploiting people, but memory hierarchies, it's okay to exploit them, okay? All right, our focus for the first part of the course has been on control and data path, the processor, right? Now we're moving over to memory, and before the course is over, we'll also have a quick look at I/O. But right now we're going to be looking at the memory, and you can see here that in this section we're going to be talking about cache, about main memory, and about secondary memory, which is our disk. Now, we talked about the power wall when we talked about processors. Now we're going to have a different wall called the memory wall. And the memory wall is the fact that processor speed and DRAM speed continue to diverge. There's a disparity which continues to grow. And you can see one graph is going up and one graph is going down. Is up good? No, up is bad. The blue line says how many clocks per DRAM access. And because clock speeds are getting faster, much faster than DRAM is, the number of clocks in a DRAM access is going up exponentially. So you can see that at this point in time, about 1,000 clock cycles for every DRAM access. So that means if you have to go to main memory and access DRAM, your processor can drink tea for 999 clock cycles. Okay? If you had a hit in cache, it would be faster. If you had a hit in register, it would be even faster. Look what's going on here. The red is clocks per instruction. So as DRAM goes this way, instruction, yani the core on the processor goes this way. And you can see now that it's 1/10 of a clock per instruction. What does that mean? We can do about 10 instructions per clock cycle, or one clock can do 10 instructions, or an instruction is 1/10 of a clock cycle. So look at that. There was a small difference, growing. Now we're at a factor of about 10,000 between what we can do in a processor in a certain time and what we can do in DRAM in a certain time. Okay, so we're going to need to have a very good memory hierarchy to help us to cover this gap. It's increasingly important for overall performance that we not waste 999 clock cycles when we don't have the data in register. So we're going to need a caching system, a memory hierarchy system in order to do this. Okay, memory technology, here's just some statistics, a little bit old, but gives you the feel for it. Static RAM, SRAM, which we talked about, of course, you remember the two basic RAM flavors, DRAM and SRAM in 223. Everybody passed that. You remember that two kind of memories, static RAM, dynamic RAM, different technologies, different access speed, different prices, different density. Here's some numbers. Access speed for static RAM is somewhere, around a nanosecond. Access speed for dynamic RAM, as you can see, is about 50 times as much. Price, quite a big difference. This is why main memory is not made out of static RAM. Well, Hoja, if this is faster, why don't we just make it all out of static RAM? Because per gigabyte, it's $2,000 to $5,000. You can't afford a PC with 4 gigabytes of static RAM. You can afford a PC with 4 gigabytes of dynamic RAM. Look at that difference. That's an enormous difference. Factor of 100. For a factor of 10 in speed, 100 in speed, there's a factor of 100 in price. Magnetic disks are way slower by a factor of 1,000,000, as you can see here, or at least 100,000, but they're also way cheaper, again by a very, very large factor. So you get what you pay for, you might say. You pay a little, you get a little speed. You pay a lot, you get a lot of speed. That's one way to look at it. The ideal memory would have this access time, but would have the capacity and cost of a disk. It would be fast like static RAM, but cheap and large like a disk. That would be the ideal. But of course, this isn't cheap, and you can't make it large at those prices. So what are we going to do? How can we solve this problem? We need it fast, and we need lots of it. And we wish it was cheap. Okay, the fact is that large memories tend to be slow, and fast memories tend to be small. Small makes them fast. We remember that principle, design principle number 1. Another thing is to consider how to create a memory that gives the illusion of being large but cheap and fast. That's what we just said over here. We would like fast but large and cheap. So, but we're going to have an illusion, right? Hokabaz, sihirbaz, get the idea? It's not going to be really, but most of the time it's going to behave like that. And the way we're going to do it is with two tricks. The trick of hierarchy and the trick of parallelism. I think you've already heard the word memory hierarchy. The cat's out of the bag. That's another English expression. The cat is out of the bag. In other words, the secret is now exposed. Yes, we're going to have a hierarchy of memories. We're going to use static RAM, we're going to use dynamic RAM, and we're going to use magnetic disk. And we're going to make it look fast if we hit frequently in the small, high level of the hierarchy, but the overall average value is going to be quite cheap and it's going to be quite large. Okay, so the overall cost will be sort of like the average cost of the lowest level, even though the performance we hope will be sort of like the average performance of the highest level. Now you can see that what's been done here. This is a really large memory hierarchy, taking advantage of the principle of locality. Let's see what we got here. Register file. Well, that's clearly the chip speed static memory from using just transistors. And then I've got some data and instruction caches, and also some translation look-aside buffers for instruction and data. And then I've got a level 2 cache. I might even have a level 3 cache, But this is all static RAM. As soon as I move off chip, I move into dynamic RAM, and then I move even beyond that to magnetic memory. And you can see that the speed in terms of numbers of cycles, and then the size in terms of bytes, and the cost from highest to lowest are all given on 3 parallel lines here. And as expected, we're talking here about terabytes at lowest cost per byte, but unfortunately access time in the tens of thousands of clock cycles, hundreds of clock cycles, tens of clock cycles for caches, and of course ones and sub-ones for things that are on chip. Similarly with size, hundreds of bytes, 10Ks of bytes, megabytes, gigabytes, terabytes. Okay? So those are some rough ideas. And you can see the hierarchy has been turned on its side. It's not a pyramid anymore. It's more like a funnel, but it goes out from here. All this is memory. You can write it, you can read it. But it's based in different technologies. Based in different technologies. Okay, let's read the part at the top. The principle of locality is the key to getting this to work. It presents the user with as much memory as is available down here in the cheapest, but because data tends to cluster together, if you can put the things you need here and here and here, you'll access it frequently, and you'll miss infrequently. You'll have a hit, and of course that'll give us high performance. When we hit here, we get our answer quick. When we miss here and have to go to here, it's tens of cycles. When it isn't here or here, we got to go to here, it's now hundreds of cycles or tens of thousands of cycles. Okay, so you can see that, and actually this is old. Remember the first slide said that DRAM is now in the thousands of clock cycles. We've passed hundreds and we're in the thousands of clock cycle range. Okay, so we'll talk more about that principle of locality, but the idea is that if I went here recently, I'm likely to go there or even there again soon, because data accesses tend to be together and code tends to be near each other. Okay, that makes sense. Okay, let's remember our technologies. Caches are going to use static RAM for speed and for technology compatibility with the chip. This is going to give us fast access time, but unfortunately it's not very dense, because to make a cell of memory takes 6 transistors versus a DRAM cell, which takes 1 transistor per cell. It burns more power. It's therefore much more expensive as a consequence. In 2008, we're looking at numbers in the thousands of dollars per gigabyte. Well, nobody buys gigabytes, of course. At those prices, you can't afford it. But the nice thing about this kind of memory, if you recall from CS-224, it's static. As long as the power is on, the content will not be lost. Of course, if you turn the power off, it's lost, but it's static. The dynamic RAM technology is quite different. If you remember from CS-224, it's much slower. Access times are quite a bit different, as you can see here. It's much higher density. It only takes 1 transistor per cell. Burns a lot less power, and it's a whole lot cheaper. But it's dynamic, which means you have to refresh the data or it forgets. Even when the power is on, dynamic memory needs refreshing or you lose the data. Ones become zeros in dynamic RAM unless it's refreshed. You have to refresh it every 8 milliseconds. That's many thousands of accesses, but you do have to refresh it. Refreshing and maintenance consumes about 1 to 2% of the capacity, the active cycles. Out of every time window of 8 milliseconds, to refresh the memory takes about 1 to 2% of it. And the addresses get divided into 2 halves, row and column. If you remember, we split the address. We have row address and column address. We give first the row, then we give the column, because you're looking at a matrix, a square matrix, remember, and you're trying to find the locations that you want. So you're going to have a row address strobe signal for strobing in the row address, and a column address strobe signal for triggering or strobing in the column address. Now, we're back to locality. This is a crucial slide. It explains the principle by which caching works. It explains the principle by which memory caching works. It explains the principle by which web caching works. It explains the principle by which database caching works. It explains the principle by which caching works. Caching is a principle. It's a computer science principle. It's not just because of CS-224 that you're talking about caching. You're going to see caching all through your education, so therefore that makes this slide a crucial principle for engineers to understand. What is caching? Caching is the idea of holding frequently used or high expected to be used information in a local, small, faster memory, so that when it is requested, you have it quickly instead of slowly. It could be held in the bigger, slower memory, but you want to hold it in the smaller, faster memory, have a copy of it, so that you will have what's called a cache hit. Now, how do you know what is likely to be used? From this much, how do I know that this much is the stuff that I should keep in my little cache? The answer is found on this slide, locality. Locality in time and locality in space. These two principles are fundamental to understanding why caching works. How could you have 4 gigabytes of memory and yet have 90% hit rates on a little 128 megabyte cache or a little, 1 megabyte cache? How could you have 90% of the things be accessed in such a tiny little cache? Only 10% misses and needs the rest of memory. How could that be? It is because of this. It's because of locality in time and locality in space. Let's have a look here. Temporal locality, or locality in time, says this. Please pay very close attention. If a memory location is requested for data or for code, then it will tend to be, tend means likely to be, probabilistically it is likely to be referenced again soon. If I went there, I'm likely to go there again soon. Now, why is that? Well, if it's data, I took it out, maybe I'm going to put it back. That's one thing. If it's code, maybe I took it out and I'm going to not took it out, I read it and I'm going to read it again in a loop. Or the procedure is going to be called more than once, okay? So if I've been there, I'm likely to be coming back soon to the same place, if it's code or data. Doesn't matter. Now, does it mean you always are coming back? No, it doesn't mean you always come back. But this location, once I know I've fetched it, is more likely than any other location to be fetched again or written to again. Now, that means that what you should do is keep the most recently accessed data items and code closer to the processor in a higher level of cache because you're likely to go access again soon. Spatial locality says that if a memory location has been referenced for code or for data, then the locations with nearby addresses, the neighbor addresses before and after it, are likely to be referenced again soon. The probability is higher if I went to X, that X plus 1, X plus 2, X minus 1, X minus 2 are likely to be referenced soon than some random location. If I went to X, then I'm likely to go nearby. So this one says if I went to X, I'm likely to go to X again. This says if I went to X, I'm likely to go to nearby to X soon. Okay, so therefore, what I should do is move blocks consisting of contiguous words into my locations closer to the processor. My locations closer to the processor, as you remember from this, is this way, moving up. If I accessed it on disk, I should keep it in DRAM. If I accessed it in DRAM, I should keep it in my level 2 cache or my level 1 caches or even in my registers. Okay? Moving things this way. Now, obviously, can everything here fit here? No. Can everything here fit here? No. Can everything fit here fit here? No. Obviously, no. We're shrinking as we go, so we've got to be selective about which ones should be cached. Okay. That's like the fundamental principle on which the whole caching hierarchy, the whole memory hierarchy is built. In fact, everything that you saw there was caching. If you want to go back again and look, main memory is a cache for disk. Level 2 SRAM is a cache for main memory. Instruction and data level 1 cache are caches for secondary cache. Register is a cache for level 1 cache. Everything that's higher is a smaller, faster subset of what's below it. So therefore, everything you see is a cache. Is this a cache? Yes, for that. Is this a cache? Yes, for that. Is this a cache? Yes, for that. Is this a cache? Yes, for those and for those. Okay? All right. Now, let's ask if you have any questions about this very profound principle. I don't want to leave anybody behind. Do not hafif getch over this. This is really, really profound and fundamental. You have to think about the programs that you have written. Think about the loops that you've written. Think about the library functions you've called and decide if you agree that this is true. Thousands and thousands, no, I should say millions and millions of programs have been researched And these principles have been found to be true over and over and over again. Is it true for every single program? No, I suppose it's possible to have some kind of program that accesses data in some really weird random way, but you'd have to really write that in a twisted way. Normal programs exhibit these characteristics. If your program never had a loop and just executed sequentially, this would still be true. Because it says after x, the neighbor x plus 1 is likely to be fetched. Amen, it sure is for code. Okay, this wouldn't be true. If you never had a loop, you wouldn't come back to the same location in code. But certainly the second one would be extremely true, wouldn't it? In fact, if you never had a branch or a loop, you would just go boo, 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 and fetching contiguous blocks of code would give you extremely high hit rates. Extremely high hit rates. Okay. So between the two of them, locality in time and locality in space, we have got the secret of very successful, shall I say, where was it here? Very successful Hokabazlik to make a memory hierarchy work for us. With high hit rates, we'll have performance like the fast little cache at the top, but we can afford to buy lots and lots of the cheap stuff at the bottom and hold everything. And now all we have to do is be a traffic manager of moving things up when they're needed and down when they're not needed. So we get motion of data and code items up the ladder and down the ladder. Okay? So that's the complication we have to manage. With a hierarchy, it's not just one memory, everything goes in, everything comes out. We've got a set of them with, you might say, cloned or duplicate copies. So the challenge becomes to manage it, and that's what I'm going to teach you from now on, is how to manage memory hierarchy and how to manage cache, how to design it right, and how to manage it. But first you have to believe that it's really true. You have to believe that this is really true, and therefore it can help us. If you say, I'm going to have a hit rate of 2%. What's the reason? What's the point? Then it means you really don't believe those. Sorry. But I'm telling you, hit rates of 80% are considered quite low. We're looking for hit rates 90, 95, 99, 99.999. We're looking for extremely high hit rates. That's what we're aiming after here. So that we get it where it's fast, even though it's a little bit expensive, but it's not very expensive because we didn't buy very much. The big one down below is the cheap one, and we got lots of it. So long as we have it, we'll get it up to where we need it in time. Okay? If we miss once, we'll make sure we never miss again, because I needed it. Oh, it's not there. Oh, it's not there. Well, then bring it up. So we'll have it now. Locality in time says if you miss once, bring it in, baby. You're going to be needing it again soon. Okay? So we'll have some misses, but we'll make sure we don't miss twice on the same thing. That's our goal. Any questions about this? Okay, I hope I've made you a believer in temporal locality and spatial locality. If you're not believing in this, then you're just going to say, what are we wasting our time doing all this memory hierarchy stuff? This is the fundamental assumption, which has been proved by research, but I want you to think about the programs you've written. That's the most important thing, is for your experience. Have you gone back to the same data structures and used them again? Reading, writing, changing? Have you gone through the same code, loops and repeated calls to functions? If you say, no, I never did any of that, then you haven't been around code very much. But if you say, yeah, that kind of sounds like the kind of programs that I've been writing, is I go there more than once. And when I do this, I'm really likely to be doing this soon or this again soon. Backward branching loops, of course. Go back and repeat the same code over and over and over and over again. How about data structures? Do you walk through arrays? Do you walk through trees? Of course you do. You know, when you're searching or sorting, you're repeatedly accessing the very same locations over and over and over again, aren't you? Okay. All right. Okay, so now let's begin to build some terminology. We're going to talk about a memory hierarchy. We have to have a language. Just with every new topic, there are words that need to be learned so that we can talk the talk. First thing is a block, or sometimes called a line. This is the minimum amount of information that is present or not present in a cache, and therefore moved up or down. The hit rate is the fraction of the time that when you request an item in the cache, you find it to be there, or request an item in a level, you find it to be at that level. And therefore, the miss rate will be 1 minus the hit rate, because either you hit or you miss. It sums up to 100%. The hit time is the time that it takes to access that level, which consists of two parts. the time to determine if you had a hit or miss and figure out it was a hit, and then the time to access the block that you wanted. Remember, you're going after blocks now. When you access an item in a level, you get a block. Miss rate is just 1 minus the hit rate. Miss penalty, instead of calling it miss time, we call it miss penalty. And it's the time to replace a block in that level with the corresponding block from a lower level. Why do we do replacement? Because of temporal locality. I tried for it now and I missed. Temporal locality says you'll probably be trying again soon, so bring it in, you won't miss again. So we always replace when we miss. So therefore, we have to have replacement time. Time to access the block in the lower level, time to transmit that lower level block up to the level that had the miss, time to insert the block into that level that had the miss, and then time to pass the block to the requester. In other words, we end up putting it in and then giving it. So it was like a miss followed by a hit. Got it? Miss, bring it in, and then give it. So it was a hit. The hit time needs to be much, much, much smaller than the miss penalty. It will be. Because the hit time is at the fast higher level. The miss penalty involves, a whole lot of things, including lower level time and transfer up time. So we're going to have miss penalties that are big and hit times that are small. Now here's a pyramid version of the memory hierarchy. This is the classic diagram. Please pay attention. It's the classic diagram. You should really put this in your mind and burn it in. This is when people say memory hierarchy, this picture jumps into their mind. We start at the top with the processor, who's actually asking for data, okay? And 4 to 8 byte items called words are given to the processor. Obviously in the processor is registers where it's actually used. So when it isn't in register, the processor says to the memory hierarchy, hey, I need it. Level 1 cache, if it's there, can pass it up. If not, level 1 cache will get it from level 2 cache, where they're a little bit larger now, 8 to 32 bytes, things that we call blocks, okay? And 1 to 4 blocks will be passed up from main memory to level 2 cache. We could also put in a level 3 cache here if we wanted. A lot of modern processors are now have got 3-level caching in static RAM before they go to the dynamic RAM. Obviously, this is dynamic RAM, this is static RAM. Okay, this is much bigger than this, so therefore it's going to be slower than this, because just bigger makes slower, even if it's the same technology. So static and small, static and big, dynamic and even bigger, magnetic and even bigger, much bigger. Okay, and now you can see that the size here is going to be kilobyte or larger, sending up to main memory, and those are called pages or disk sectors, right? So a disk sector is the name here, and a page is the name here. They're large compared to these. This is 1 to 4 blocks, where blocks are anywhere in this range. So we're talking hundreds of bytes. Now we're talking thousands of bytes. So the size of the element gets smaller as we go up this way here. So word, block, multiple blocks, page, disk sector even. Okay? And you can see that the size of the memory at each level keeps getting bigger. So that, therefore, we have the pyramid effect. Finally, what I'd like to say is the fact that everything in this level is included in this level. This is a subset of this. Whatever's here also is here. Whatever's here also is here. This is a subset of that. This is a subset of that. So therefore, the following is true. Whatever is in level 1 cache is a subset of what's in level 2 cache, which is a subset of what's in main memory, and that's a subset of what is in secondary memory. Okay? So it's not either or, it's both and. If an item is here, it will also be here. All right, now cache memory is the level that is closest to the CPU, or levels, if we have multiple. Let's say that we have an access string, x1, x2, xn. Okay? So we've got a string of accesses. Before the reference to xn, it looks like this. And then we've made these accesses, and our cache looks like this. And you can see that xn is not present. After the reference to xn, because we needed it, we bring it in, and now it's present in our cache as well. How do we know if data is present, and where do we look, are the two questions that we want to answer. How do we know if it's present, and where do we look? Those are fundamental questions to organizing the memory hierarchy and the cache. How is the hierarchy managed? Management, as you know, Unit Menlik, who's going to run the show? Who's the boss? Who decides if something is in register or in memory? Well, you know, we've done a lot of load word and store word instructions. That's done by the programmer, or at least by the compiler who generated the assembly language that generated the loads and stores. Who decides if something's in cache or in main memory? You see what's going on? These are the transfers between levels. Oh, I didn't mention this, but I should say, we never jump a level. Things here don't go straight to there. Main memory items can move up to level 2. Level 2 items can move down to main memory. There's no communication direct between non-adjacent levels. If something in secondary needs to get to level 1, it gets there by going to main memory, and then main memory sends it to level 2, and level 2 sends it to level 1. We don't skip over levels in our memory hierarchy. So having said that, the communications are therefore between these two, between these two, between these two. And so the question is, who manages? All right, the compiler decided whether something needs to be in main memory or register, or maybe the programmer, if it was writing in assembly level. When it's between cache and main memory, then a special hardware called a cache controller manages that. The cache controller is a finite state machine, sequential circuit, classic CS-224 design machine that decides what to move and when to move it. Okay? So it's just simply doing memory reads and memory writes to pull things from main memory into cache or send them back down. Okay, now between main memory and disk, who decides when things need to move? Those pages or disk sectors, how is that managed? And it's managed by the operating system. If it's a virtual memory, that's an operating system function. You'll learn about that next year in CS-224. It's also managed by hardware called the translation look-aside buffer for part of it, because there's a virtual address to physical address mapping. And we're going to find that there's a little cache called the translation look-aside buffer. If you didn't notice, on this slide right here, this says DTLB because it's near the data cache, so that means it's the data translation look-aside buffer. And that says ITLB because it's next to the instruction cache. That's the instruction translation look-aside buffer. Translation look-aside buffer has been defined for you now as a hardware which assists the operating system to manage virtual memory to physical memory mapping. Okay, so we've got software in the operating system managing it along with some hardware support, and finally the programmer, because the programmer is deciding if he's going to open or read or write files. If you do those, you're saying something on disk, please access it. Of course, that means it's going to have to come into main memory. We can never directly access disk from a user program, so when the user says I want something in a file, that means bring it into main memory please, so my program can have access to it. So actually the most complicated one is this. This one's buried in hardware. It's designed and done by hardware design engineers, and this one the compiler has a lot to do with. Okay, any questions about management of the hierarchy? Who moves things around from place to place? Okay, if you have multi-level caches, then this needs to be a fancy smart hardware, because you got level 1, level 2, maybe even level 3, but all this is going to be managed in hardware, not in software. All right, back to our two questions. How do we know where something is? Or do we know if it's in a cache, yes or no? And if it is there, how do we find it? Fundamental two questions. Their answers to those questions are determined by the architecture of the caches. And I'm now about to embark in a series of slides explaining the architecture of caches. There's different architectural options, and you're just about to begin them right now. The first one is called direct map cache, but it goes on and on and on. So what we're doing now is beginning to realize that architecture and design are the answers to the questions. If you want to answer the question this way, your design will be like this. If you want to answer the question a different way, your design will be like this. Or you might look at it the other way. If your design is this way, then your answer to the question is this. But if your design is this way, then your answer to the question is that. But these two questions are the top level over which the designs that come out of these architectural options are based. So that's what I'm about to explain is architectural options, designs, and the differing answers to the questions that they're going to give. But the questions are what we're trying to answer. Okay? If you have a direct map cache, which is one of the three major options that I'm about to show, every memory block is mapped to exactly one block in the cache. Every memory block, if it's going to be in cache, has exactly one place it's going to be. Well, obviously, there's more memory than there is cache. So there's more memory blocks than there are cache blocks. So it should be obvious that many to one is the mapping. It's a many to one mapping. But every place in memory knows if I'm in cache, I'm going to be there. And that means if you say I'm going to be in cache at X and I say I'm going to be at cache at X, you know what? We can't both be in cache at the same time. We could have a conflict. Because if you need to be in cache, you're going to be at X. You are direct mapped. You can't be at X minus 1 or X plus 3. You'll be at X. And if my mapping says if I'm in I need to be at X, then we can't both be at X at the same time. So direct mapping has a many to one mapping from memory blocks to cache blocks. Memory is bigger, cache is smaller, more memory blocks, less cache blocks. You can see it's going to be many to one. So therefore, lots of lower level blocks must share blocks in the cache. But it doesn't mean share like Buiren Gel, Wilsukishijaziani. No, it doesn't mean like that. It means that we're mapped to the same one, Yasen, Yaben. It's not really sharing. It just means they will map to the same place and it's either or. Now, the mapping is pretty simple. The second question is, if it's in there, how do you find it? The mapping is very simple. You take the block address and you go modulo that by the number of blocks in the cache. So your memory block address modulo however many blocks there are in the cache, 8, 4, 1024, whatever. Now, in addition to that, since there's possible multiple mappings, you could be there and I could be there, we're going to need to have a tag associated with each cache block that contains the address information, which is the upper portion. Remember, when you do modulo, you lose the upper bits and keep the lower bits, right? Everybody know that? When you do modulo, you lose the upper bits, keep the lower bits? You don't know that? Oh, well then we better do a little modulo arithmetic on the board to remind you about how it works. I thought you knew modulo arithmetic. All right, let's try this. Anything x mod 4 means, by definition, means what? The remainder of x divided by 4, right? Okay, great. So the remainder can be either 0 or 1 or 2 or 3. Remainder can't be 4. That would be in the quotient. So it means the remainder. That's the definition of mod. This operation mod is defined that way. Great. So if I take this binary string and I say mod 4, what are my possible remainders? 0, 0, 0, 1, 1, 0, or 1, 1. Where do I find the remainder? Where do I find the mod? I just look here. That's all I have to do. I don't need that. That's unimportant information. I look at the last bits. That's the result of the mod. So the mod operator will always take the lower bits and throw away the higher bits. Is that clear to everybody? Do I need to do more examples so you're convinced that that's true? How about we take this one? 10110001 mod 16. What's the answer to that? Instantly. Zip, zip, there we go. That's the answer. Never mind that. That's not important. Because it's mod 16, I'm interested in the remainder bits. How many possible remainders are there? Sifr, 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 done, beer, 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 akadar, right? So mod is piece of cake in binary arithmetic. You knew that, didn't you? You knew that already. Yeah, you didn't need that a review. Well, then tell me. No, sir, we know mod very well. Don't waste time on the board and getting your pens out. We know mod. Say things. Help me out. Don't make me think that your education was exic on important things like this. All right, now let's come back to here. So therefore, when I do this operation, what I'm going to get, obviously, is the remainder bits. But your remainder bits and my remainder bits are the same. If you map to that cache location and I map to that cache location, it means that we have the same lower bits. So what's different about my block address and your block address? The upper bits. That's how I'm me and you're you. If our addresses are completely the same, then we're not different cache blocks. We're the same cache block. Got it? We're together in memory. So to be different means our upper bits are different, but our lower bits are the same, so we map to the same location in cache. Yeah. So what this is saying is the tag is the rest of the information. This part that we threw away, that's the tag that makes me, me. Okay? And that tag will contain the address information, the upper portion of the address, required to identify the block to answer question 1. How do you know if the data item is in cache? Let's try this. Let's say you map to cache location 5 and I map to cache location 5. And we say, there's something in cache location 5. Is it mine? The only way to know is to hold the tag of my upper bits. And if it's there, then, oh yeah, it's Williams. No, it's not Williams. It belongs to, what's your name? It belongs to Ayrton because it's his tag bits. The tag is the Kimlik, the Kishi cell ID, right? The upper part of it, obviously. The lower part of it is related to being in that cache block. All right, let's have a little quick example and then we'll take a break. I want you to understand this first big technical point. Now we've moved down from kushbakish to real detail. We're really in the detail here. So you'll have to concentrate. I know it's 4:30 on a Tuesday afternoon. The room's kind of hot and stuffy and people are yawning and all, but please focus. If you miss this, you're going to just be kopmush. You want to be kopmush from the course? This is a great chapter to learn how to cope, right? Just cope completely. Man, you'll be so lost. You get a big 0 on the final exam, come back next year, hojit, seni yokadar çok sevdim ki. Yani I'm back. I love your course. I want to take it 5 times. No, I'm just joking. All right, here we go. Look, the cache contains data stored, of course. That's the purpose of it. And it contains a tag to know who the data belongs to, and a valid bit. So there's what we have at cache location 0. That's the first cache block. There's the next cache block. There's the next cache block. There's the next cache block. So my cache location holds 4 things. Now my full memory, as you can see here, holds 16 things. So if this is a direct map cache, it's a 4-to-1 mapping. And so when I take this main memory address and I mod it, mod 4, because that's the size of my cache, this is going to go, or map to, cache block 00. This one's going to map to cache block 01. This one's going to map to cache block 10. This one's going to map to cache block 11. This one's going to map to cache block 00. Do we got it? You see how it works? Okay, so therefore this one, and this one, and this one, and this one are the 4 that all map. You can even see their arrows. They all map to this red, cache block 00. And that's why their colors are red. Everybody see that? And then the next ones, which have the modulo of 01 are blue, and that one, and that one, and that one, and that one will all map to this cache block 01. It's a 4-to-1 mapping in this very simple little pedagogical example. Obviously not in real-world examples. It's not 4-to-1. It might be 4,000-to-1 or 4 million-to-1 because cache can be quite a bit smaller than the level below it, right? If you've got 4 gigabytes of main memory, I seriously doubt you have a gigabyte cache. I seriously doubt you have a gigabyte cache. You might not even have a 256 megabyte cache. You might have a 256 kilobyte cache. Or you might have a 2 megabyte cache. So the mapping is going to be very heavy, n to 1 with large n. Do we understand that principle? Okay. All right. The next thing I want you to understand is that the 2 lower order bits are the cache block index number. So what are these upper bits? So what are those? TAG, tag. They're the tag bits. So the tag of this is 00. Does everybody notice that's different than the tag of this? Look, they're both red. They both have the same cache block index 00, but they don't have the same tag. That means you are you and I am I. And that's my Kimlik. That's my ID. That's how I know that if I'm in cache, I'm different than you. So we're going to store not only the data here, if we store main location 000, we're also going to store the tag 00 here so that we know it's not belonging to this one or to this one or to this one. The tag is the personal identification. And it separates out n to 1 so that it can be 1 to 1 so that you can know it's you, your data. Got it? N to 1 says we're all confused. It could be any of us. But with a tag, now I have an ID number. Hey, see me? That's me. That's my identification. Okay? Do we understand that principle? Okay, good. So the first question is it there? Is the thing I'm looking for there in the cache? So let's say that I'm looking for this location. No, let's pick a different one. Yeah, that's okay, that green one. So I'm looking for this. Is 0011 in the cache right now? Well, first question is, I know where to look, and it's where? Right here. And there's something there, but is it what I'm looking for? So I also have to check out, is the tag 00? And if yes, and if the valid bit is 1, bingo, I have a hit. Yes, it's in the cache. Okay, so that's how I know, is it there? Second question is, how do I find it? Okay, I use the 2 lower order memory address bits, which are the index, to determine which cache block or which, it is in, the modulo number of the thing. So in other words, we already did that. This 11 says, oh, go look here. That's where you'll find it. If it's in, it's there. If it's in, it's there. How do I know it's in? Check this in the proper place, not all of them, just the one in the proper place against the one that you're looking for, and the valid bit. One more time. The block address of the memory block moduloed with the number of blocks in the cache. In this case, it was 4 blocks, so we did everything mod 4. Any questions? All right, I know some of you have lots of questions. You're just too shy to ask in front of the class, especially on video camera where it's being broadcast to every human on planet Earth. So maybe you can come up during the break if you have questions. Okay, Ur's got one right now. I'm going to say come up during break. So anybody has questions, I'll be here. Let's take a 10-minute break. Let's also cool down the room, get some oxygen. With the back row people, please open the windows. Come back in 10, and we'll continue.